Hi everyone, thank you for joining our third webinar in our webinar series. Today's session will be a technical overview of our Adsorbent media with our Chief Technology Officer, Jess, as our host. Before we start, some housekeeping notes. This session will be recorded and uploaded onto our YouTube channel afterwards. So if you want to go back and rewatch things, you can do that. You're more than welcome to. This should last between 20 and 30 minutes with a Q&A session at the end. Feel free to make use of the chat box in order to ask those questions. That's how we'll run the Q&A session. And with that, I'll hand it over to Jess to share her screen and go through her deck.
Thanks, Ade. Let me see if I can get... Oh, sharing is not turned on, apparently.
Are you able to now?
I'll try, hang on. Yes, I certainly am. Brilliant. Thank you so much, Ade.
No problem.
Let's hope that everybody can see it. Can you confirm that you can see my slides?
I can see your slides.
Great. Wonderful. Well, welcome everybody, and thank you so much. We've got some thumbs up there. That's great. Thank you. That's really good feedback because I can't see anyone, but I shall continue to talk to the wall. Thank you all so much for signing up to join this webinar today, and hopefully I'll be able to give you a little overview of our media with a little bit more technical, sort of a more technical approach than perhaps some of the previous webinars that we've done at Puraffinity. Um, and yeah, please do interact with the chat so that any questions that you have, there's plenty of time for Q&A at the end, and I will be able to see those coming through and we'll be able to pose those to me. So, as I said, it's a technical overview of Puraffinity's adsorbent media, but I thought I'd quickly start with a meet me because it's sometimes nice to know who's talking to you. Um, Hi, I'm Jess. I am Puraffinity's CTO. I joined in September 2024. Um, I'm not a chemist. I am not a salesperson. I am a materials scientist by background. And I now really enjoy working in purposeful organizations and particularly in Pure Affinity, but environmentally focused, purposeful organizations with a water side seems to be my niche right now. Um, I love working with big global teams and trying to solve real problems. And that's what brought me to Pure Affinity. And the team here are certainly working hard to do that. Um, so, a little bit about the problem. Hopefully, most of you on the webinar know about PFAS, but for those that are less clear, it is a family of chemicals that are very persistent, which means they don't break down in the natural environment. So the media typically calls them forever chemicals. Normally, when I tell somebody, oh, I make products that remove PFAS from water, you get a blank stare. And then when you say toxic forever chemicals, then there are nods and there's a big media presence there. So do not break down in the natural environment. They are bioaccumulative. They bind to proteins within the human body and can start to cause damage because of that, and they are everywhere. We have, as humans, used them for all sorts of things that arguably we shouldn't have. I just want to be really clear that it's my view and Pure Affinity's view that we are not a solution to this problem on our own. We are part of an ecosystem of solutions. Really, we need to be really carefully regulating how these chemicals are used and what they are used in. Of course, they have amazing properties, and in certain circumstances, I am sure that they are the right approach, but probably not for waterproofing your waterproof rain jackets or on your non-stick frying pans. So, just a little note on the right-hand side about the different types of human health concerns that these PFAS have been linked to in the science. Um, it's a relatively under-researched area. We know a lot about PFOS and PFOA because those have been the most pervasively used of the PFAS species. But so I think it's quite likely that other things will come to the surface, but we know that they are damaging to humans. And that's the kind of call to action, really. That's where we want to have impact ultimately. So I just wanted to pick up on that first bullet point, pervasive. Um, I've chosen to go for the US, but we have an equivalent slide in a minute for America, for Europe, sorry. Um, as you can see from these slides, and I've included um, my source links here. This is publicly available data. There are known PFAS contamination sites all over the United States of America, in drinking water. Not all, so the right-hand side being below the current proposed drinking water limits, but even still, a very high number of contaminated drinking water sites and also a lot of environmental water that is contaminated, known to be contaminated. And as you can see, there are a lot of those are military sites, which is typically from the use of aqueous film forming foams for fires and that sort of thing. Um, and this is really recent data. This is August 25, so pretty recent. Um, the European data is a little bit less recent, so about this time last year. And it's also a little patchier because this was a collaboration between a handful of countries that were doing sort of more targeted PFAS testing. So as you can see, lots of blobs there over places like Denmark and France and Germany and the UK. But again, a lot of points and not all at very high concentrations, but nonetheless something should be worried about. So we want to fix this or be part of the solution at least. Um, so just talking a little bit about why Puraffinity exists and is targeting this space. Typically, there is legacy technology being used to target and control PFAS in water. Um, Most widely, granular activated carbon and ion exchange resins. Now, these are very well established water treatment media. They were both developed in the middle of the 40s, 30s, around that time initially. And obviously there has been some development since, although arguably not loads. Um, they are broad spectrum adsorbents. So granular activated carbon is fantastic for organics, particularly volatile organic compounds, industrial and agricultural chemicals, pesticides, lots of different things. It happens to work on some PFAS species as well. Ion exchange resin, similarly, really useful for any waterborne contaminants that can be attracted through electrostatic interactions. So really great for nitrates, sulfates, perchlorate, fluoride, ammonium, lots of things that you find in water. Makes perfect sense. Brilliant at those things. Some metals. Again, works for some PFAS species. And different products will work better or worse for different species. That's fair enough. Typical empty bed contact times for granular activated carbon of around 20 minutes for PFAS and around 5 or 7 minutes for ion exchange resin for PFAS. So the empty bed contact time being the amount of time that the water needs to be in contact with the media for the PFAS to be adsorbed to the surface of the media. So that kinetics, if you will, how fast the attraction takes place. Not great on short chain PFAS, either of these products. Some ion exchange resins a little better. And because you need a 20-minute empty bed contact time, typically you need really high volumes of this media in order to treat a big volume of water. And there are some regulations around particularly granular activated carbon and how much contact time is required in certain countries for effective PFAS removal. Um, so these I would describe a little bit as jack of all trades. Doesn't mean they won't function against PFAS, but Puraffinity is taking a different approach. So we are taking a much more targeted and designed approach to trying to tackle PFAS. So where granular activated carbon works as a highly porous and hydrophobic solid and relies on those hydrophobic interactions to attract PFAS, and then its high porosity to have a high surface area so that it can absorb PFAS. And ion exchange resin, it has some hydrophobicity, but predominantly functions on an electrostatic interaction with those charged sites within the polymeric resin. Um, Puraffinity's media has a porous and inorganic substrate, a mineral, effectively. And then we apply a targeted surface chemistry that acts with a quite interesting combination of hydrophobic and electrostatic interactions. We know that granulated activated carbon works hydrophobically. We know that ion exchange resin works predominantly electrostatically. Why not combine those two so that we can make the best of both? So our coating is covalently bonded to our porous inorganic substrate. It's quite a thin layer. The pores again help with surface area, and we make the most of the combination of hydrophobicity and electrostatic interactions. Um, just to go one step further than that, so we're using a predominantly alumina substrates, although we are researching some other types of substrate too. And what we're doing effectively with our targeted chemistry is creating a thin polymer layer and then a hydrophobic layer on the top. And the linker there is binding those two things to the surface of the alumina. So as you can see, it's a really carefully thought out layer by layer approach to try to maximize performance with PFAS. And specifically at the moment, we are talking about longer chain PFAS, EPA6 type PFAS species, but we are also actively developing products for other types of PFAS and including short chain PFAS. So what we know from the work that we've done and the research that we've done is that it is the combination of substrate and surface chemistry that leads to great performance. So we know that if we change the substrate but keep the chemistry the same, the performance changes. And we also know that if we keep the substrate the same and change the chemistry, the performance changes, which is perhaps less of a surprise. So it's not just the surface chemistry that is having the impact, it is also the substrate. And it is that combination that's important. So in terms of our substrate, we get, well, to begin with, our substrate has a particle size distribution, which means that we're talking about a D10 between 310 and 340 microns, and a D50 in the 530 to 630 range. So it's not dissimilar to an ion exchange resin, actually. But our substrate is a mineral, and it is both macro and mesoporous, meaning it has large pores and small pores, which provides a really high surface area and also enables flow in use, which helps operationally because this is not just about, wow, we've got this great chemistry that attracts PFAS, but we're also very aware that our product needs to work really well for our customers and it needs to be easy to handle and use in systems in the field. So what we're targeting here is something that is chemically really active and works really well for PFAS, but also a product that functions well and in particular doesn't lead to really big problems with pressure drop in a pumped system. So it's well suited to backwashing. It responds brilliantly to backwashing actually. And it's not dissimilar to something that you might use already like an ion exchange resin in that you can flow water through it happily. It's a bit heavier than a typical resin or a carbon at a specific gravity of about 0.9. I just want to talk a little bit. So the substrate is alumina, which is a mineral. The coating is a thin polymeric coating, multi-layered. And just to be really clear, there is a real benefit to that from an environmental perspective. So the total carbon footprint of our media is roughly half what you would expect from a activated carbon system. Now, this is predominantly because you can use a lot less of our media. Um, and I'll get into that in a little bit in the next slide. But ultimately, you can use about 1/20th the mass of our media or 1/40th the volume of our media to do the same job or the equivalent job of a carbon system. And as a consequence, you end up with much less media. Um, Obviously, because you're not using a whole bunch of carbon or polymers, it's also got a much lower carbon footprint. Um, and that those numbers are real, they're not fingers in the air. We have actually replaced a carbon system for a client with our G400, Puretex G400 Plus media, and we replaced a 4,000 litre system with a 180 litre system. So that gives you real clarity on that difference. And we haven't included incineration as an end of life process here, but of course you would be incinerating 1/40th the volume of media. So that would further improve the CO2 performance. Um, in terms of performance differentiation, ultimately, um, because we've got this really targeted approach and we are leveraging both hydrophobic and electrostatic interactions, as I mentioned earlier, what it leads to is startlingly fast kinetics. So instead of the empty bed contact times of 20 minutes for carbon and 5 to 7 minutes for ion exchange that I talked about earlier, what we're actually talking about for our media is somewhere between 15 and 90 seconds. Um, and yes, we're talking seconds, not minutes. It is that much faster. And that offers huge benefits for system design. And in fact, it's a kind of completely different approach to system design. So you would never really plan to put Puraffinity's media into massive great vessels like you would carbon. The system's footprints can be just so much smaller. So when space is at a premium, our product is a really great option. Um, it also means that it could be portable. So if you didn't need a system to be in place for a very long time, you wouldn't have to build big infrastructure because you're talking about much smaller vessels and much smaller systems, which can be built on skids, on trailers, in containers, so that you can move them around easily and more flexibly. Um, we're using 1/40th of the media volume for equivalent performance. So there's a lower environmental impact, as discussed. The disposal costs are lower, and it's ideal for things like point of use and point of entry systems, where you have got a real space premium because you're trying to put something in someone's home in a plant room or in a plant room in a building or under a sink. And of course, you don't need to hold a big volume of water if your empty bed contact time is only 15 seconds. Um, and of course, this smaller system footprint also leads to reduced CapEx and OpEx because you're saving on infrastructure. You're able to use off-the-shelf components, build portable skids, and the media replacement is so much easier. You can simply plug and play vessel exchange. So take one vessel out, put the new one in, and then you can deal with all of that waste later. Whereas with something like a carbon system, you are bringing trailers on site and you are pumping that carbon out of those vessels and putting new carbon in. That's a big logistical effort, and the system downtime is significant. So all of this targeted approach is not only designed to do a great job with PFAS, which it does, but it's also designed to make it really easy to use and to open up the possibility of treating PFAS to customers who simply cannot fit the infrastructure needed for these legacy medias. Um, just a little word on approvals. We have passed all the OECD tests that are listed on the left-hand side there. And we also have UK and EU REACH approval in the 10 to 100 ton band. Um, and we're working on drinking water approvals in a range of countries at the moment. Um, I've spoken quite a bit about this targeted approach. we take the science really seriously. Of course, I can't tell you loads about it because there is pending IP and other trade secrets and proprietary information that we would be stupid to share in a webinar on LinkedIn. But I just wanted to, highlight a few of our key collaborators. We are developing methods to measure PFAS better. We are developing methods to assess the other chemistry that's part of our media. We are working with people that know about scaling up media. We have good capacity now for manufacture. And we are always trying to push the boundaries. So we have products available now that are great for your EPA 6 type species, and we are continuing to innovate and to sponsor PhDs and to build academic collaborations to tackle and to develop products that will tackle your PFAS problems that are emerging or will likely be there in the future. So we would always appreciate anyone who wants to contact us with difficult and thorny PFAS problems that other solutions don't meet yet, because we would like to develop products that people want and that actually, as I said at the beginning, meet a problem, solve a problem, meet a need. So please don't hesitate to be in touch if you have thoughts on that. Um, just a word on our sales team. So as I said at the beginning, I'm not a salesperson. This is slightly uncomfortable for me because I'm not, but hence I wanted to do it more technically. But we do have a lovely bunch of sales people, both in for Europe and for North America. Well, and of course we cover wherever in the world that you are. So contact details available here, but also you can go to the Puraffinity website to find how to contact us. And as if by magic, there is the website as well as our info@puraffinity.com email address if you would like to be in touch. So, Ade, I hope we've got some questions. Maybe we haven't.
We do
Maybe I've
have
been
some
really
questions.
clear.
We have a few. So, are there any limitations users should be aware of when using Puriffinity's adsorbent media?
Yes, there are, as there are with any adsorbents. So we have working pH ranges and we have clarity on which other types of co-contaminants may reduce the effectiveness or efficacy of our medias. So um, particularly high TOC in the water would be something that we would need to assess, and so would certain types of metals or other contaminants. So it's not that we can't cope with them, it just depends on the level. We've tried to test across a wide range of co-contaminants, including things like chlorine and chloramine and different ionic salts. But it's a kind of case by case basis. So what we would typically do with a client is assess the kind of water that they want to treat and make recommendations. And sometimes that will mean some level of pre-treatment to remove things that are easy to remove with cheap upstream systems so that we're getting mostly PFAS. But we are fine with quite a few different co-contaminants at various different levels. So it's
How,
a horses for
sorry.
courses, Ade, that's the answer. Sorry.
Yeah, no problem. How effective is the adsorbent media for short chain PFAS, and how effective is it in complex water such as landfill leachate water?
So we've had some really interesting client trials on landfill leachate that we would be able to share if you were under NDA with us. Um, so we can be quite effective. Certainly, we were compared to an ion exchange resin and came out considerably more effective for the same application on a landfill leachate site quite recently. Um, sorry, short chain PFAS. Some are better than others. So we are pretty good on some four carbon chain species like PFBS, for example. Like most other media right now, we are not great at PFBA, and I can be honest about that. It we have some impact, perhaps arguably better impact than the legacy media. But it'll depend on the overall cocktail of PFAS that's in there. And we are working on new media products that are targeting short chain.
How does the pH of the matrix affect efficiency, and how long does it last in real world conditions? Do you have any examples?
So we don't have a problem with the efficacy with pH, but alumina doesn't like very alkaline or very acid um, solutions, so the substrate starts to break down. So we would typically say that the working range for our media is between 2 and 10 in a pH setting. And sorry, what was the second half of that question, Ade?
How long does it last in real world conditions?
It depends on all sorts of different factors. It depends on your flow rate, it depends on your system size, it depends on the specific empty bed contact time that we run, it depends on the concentration of PFAS that you have at the inlet and what you need at the outlet. We are always going to be governed by your target breakthrough versus the inlet concentration. So there is not, how long it lasts is completely bespoke to the customer.
Do you have any thoughts or insights on the layered double hydroxide material for filtering PFAS that came out of Rice University recently?
I thought it looked really interesting, but I will be watching with interest because I want to see how well it scales. I think quite often, as I said in one of my previous slides, we're very aware that having something that works brilliantly for PFAS doesn't necessarily mean that it's great operationally. And if it's not practical to apply, it will be more hassle than it's worth. So that's one of the things that's on my watch list to keep an eye on to see how it progresses into sort of bigger scale use.
Is it possible to desorb PFAS and reuse the material, or do you need to incinerate it after use? I'm working on low energy PFAS destruction.
It depends on the media. So we have some media where it is absolutely possible to desorb the PFAS, but we do find that the better the PFAS sticks to the media, the harder it is to dissolve it. And that hasn't been a huge priority because most destruction technologies are not super mature at the moment. We have done quite a lot of work with a variety of different destruction companies and destruction techniques to prove that our media is compatible. But the truth is that in the industry at the moment, most destruction is thermal and is done by incineration. We've had some other really good results with other solid state destruction techniques as well, though, where you don't need to spend the effort, money, and energy to desorb the PFAS, but instead you can destroy the media and the PFAS, but it's not necessarily through thermal means.
How is production cost compared to other known adsorbents? I'm assuming manufacturing costs, they mean.
We are more expensive than other media. There is no question of that, but you need 1/40th the volume. So usually the total cost of ownership is similar or ideally a bit less. And we are, well, the sales team in particular are really great at really truly understanding customers' needs. And if we are not the right choice for you, we will be honest about it.
So I think that ties nicely to this question. What should customers consider when integrating this media into their existing infrastructure?
Well, I mean, it's a no-brainer for some customers, Ade, because we have some customers that have come to us who simply cannot fit a carbon or an ion exchange system on their site because they're really tight for space because they can't get the vehicles with the media in there because they can't build a building to put the carbon vessels in because they're somewhere where it snows in the winter and it just can't function. So that's a no-brainer. It opens up PFAS treatment to those types of client. For other people, it's about total cost of ownership. So quite often people go straight to how much is your media per kilo, but that is not the question because if you're using 1/40th the amount of media, then or 1/20th the mass of media, then suddenly that isn't necessarily the deciding factor anymore. Typically, we use 1/20th the media. The vessels are smaller, they are manageable by hand, um, and usually we last longer as well. We can build the system to be smaller and last longer as well. So the worked example that I had on my previous slide, 4,000 kilos of carbon versus 180 kilos of Puretech media, and we lasted 1.5 times the time that carbon lasted. So it's about total cost of ownership. It's about the operational costs. It's about the capex. A lot of organisations can work with OPEX costs over the longer term, but find capex a real challenge. Puraffinity has the ability to help you design a system that works for your water. And we're also very happy to specify hardware and even are building systems to um, rent or provide um, treatment skids. So that could be a really cost-effective solution if you've got limitations in capex budget, for example. Um, so those are the kinds of things to think about. It's about how long you need to treat the water for, what your outlet needs are, and they can be really tricky. So I showed those maps earlier, of the United States and of Europe and the different sites. Let me be really clear, the regulations are really variable across the world. In the States, there's a federal limit of 4 parts per trillion for PFOA and for PFOS, but lots of other states are setting very much tighter limits for both drinking water and surface water, and many are also operating discharge permitting, which means that on a site-by-site basis, there will be limits to the amount of different species of PFAS that you can have in that effluent water. And it's the same in Europe, and particularly I would note Denmark, the Flanders region of Belgium, and the Veneto region of Italy are very strict around not just drinking water PFAS, but also um, any waters that are being um, discharged into the environment. So it's all about understanding the context of the treatment that you need to install, and we can help with that.
Do you have case studies to show that adsorbent has effectively treated complex matrices, AFFF, etc.?
We have some, and we are working on more. So last year we ran over 50 different lab and pilot scale tests with different customers. We're working with them on which results we can share. They're happy for us to share. So we have a couple of case studies that are already out. Ade, I think you've probably got more information about those than I have.
Yeah, we do
Yeah.
have some case studies on the website. If you go over to the website and go to the case study section, you can input your information and download them. And we do have a AFFF case study as well.
Yeah, and there is more coming because, as you can imagine, as we start working with these pilots, with landfill leachate, with AFFF, with very low concentration PFAS, with weird combinations of PFAS, all of those things build up over time as customers pilot the media. So more coming every quarter this year.
Would I still need GAC for other pollutants?
It really depends what's in your water. Possibly. You might find that the thing is, if you've got loads of other pollutants that are going to that would have an impact on our media, then you're probably better off using GAC to catch those. Let the PFAS push through the GAC, which it will quickly, but the GAC will probably still be active for a lot of your other organic contaminants, and then letting us mop up the PFAS, which we can do for much longer than GAG. But it really does depend. There will be plenty of water systems out there where where GAG wouldn't be required.
And last two questions, because I'm cautious of the time. Do you have RSSCT capabilities?
No, because our media is a surface coated media, rapid small scale column tests are not really viable. Actually, the most recent research is showing that rapid small scale column tests are not very good at predicting PFAS performance for any media. I know they are commonly used for carbon in particular, for lots of other contaminants, but the latest science seems to indicate that they are not very good predictors of full-scale performance for even for GAC with PFAS. But as you can imagine, when you're using a rapid small-scale column test, what you tend to do is grind up the media. And if your media is a through-thickness media, like the carbon or the ion exchange resin, then you just get small particles of exactly the same media. But because our media is a surface-coated media, what you do is expose the core of the media, which is then not coated with the active polymer. So rapid small-scale column tests are not a good indicator of performance for Puraffinity's type of media.
And then I think this is a nice question to end on. How do you see your technology evolving over the next few years?
That's a lovely question. Thank you, whoever asked that. Um, as I said, we want to solve problems, and the best thing that we can have is feedback from the industry on those problems that as yet do not have solutions or do not have satisfactory solutions. We are expecting to develop and are developing a range of media solutions, predominantly targeting PFAS, but different species and groups of PFAS, so that we can try to meet the needs of the industry that is trying to treat those in water. So we're trying to anticipate that need, and we are working hard to develop those types of product. And that makes my research chemists very, very happy.
Thanks, Jess. So that is the end of our session. If you do have any more questions, please feel free to reach out to us on info@puraffinity.com. And if you would like to go to our website to download the case studies or just to have a browse to see what is going on over there, please feel free to go over to our website too. Thank you, Jess, for taking the time out of your very busy schedule to host this session.
My
And
pleasure.
we hope to see some of you again in our next one.